Hi, I'm Justin.
And I'm Andy Jones, and we're researching white light profilometry.
Hey Andy, I'm super curious about profilometry, but I have no idea where to even begin. Could you break it down for me?
Sure, Justin, but let's start small. What is light?
Well, from what I know I know that it's kind of similar to sound waves or beach waves, except for it's electromagnetic waves. And so each color corresponds to a specific wavelength.
Very good. One of the interesting things about waves is that they can overlap and interfere with each other. That means that if they're aligned right, the light becomes brighter, and if they are aligned wrong, they cancel each other out. Have you heard of interferometry before?
That sounds like you're measuring the interference, like in the Michelson interferometer. You can split the light into two mirrors so that it can reflect back on itself. This means you get more interference that makes bright and dark fringes that you can see.
Exactly. Depending on the color of the light and the position of the mirrors, you get different patterns and sizes. White light needs to be especially precise since the different colors wash out the fringes very easily. Why don't we try it and see what it looks like?
Let's do it.
Okay, wait, so my result looks different than yours. What's going on here?
This is where profilometry comes in. Think of the Michelson. It splits the light and uses two mirrors to make it seem like it's coming from different places. White fringes only appear when the mirrors are to exactly the same distance. How might a tilted mirror change that?
I mean, I guess a tilted mirror won't have just one distance. It has one close side and a far side. And so that would mean the fringes only appear on the side of the mirror that's exactly the same distance, something that has no optical path difference. Does this mean profilometry?
You've got it. We can track the fringes as we move the mirror forward, which shows us where the mirror surface is. For this mirror, it's very flat but tilted at a small angle. The other one has a much larger angle, but it's also uneven. See here where part of the fringes jumps ahead of the others?
Oh, so that's a place where the mirror has a depression and takes a while to come out. That means that this spot has a steep angle, right?
Exactly so. If we take the video and process it the right way, we can even calculate where the surface is by looking at different slices as the displacement changes. See these thick and thin fringes? That's the mirror when you look at it from the side.
If you're as interested in profilometry as I am, you probably want to know what it's used for. This is a real-world profilometer that we got to use. Special thanks to Lumi, who showed us how it works.
This looks like a microscope, but it flashes light to make fringes rather than letting you look through it. What you see here is the edge of a microscope slide.
The computer takes those fringes and processes them just like we showed you. That gives us the profile of whatever we're looking at. Here is a particular interesting one that's basically just up and down. Can you guess what this is?
This is the 2 embossed on a penny. The profilometer is so precise that something so small still looks like a huge cliff.
If you want to see big breakthroughs in profilometry, Dr. Kim is the one to ask. Not only does he manufacture classroom-sized mirrors, he's actively pushing the limits of what we can do with profilometry. Not only can you use it to check that the final product is exactly the way it should be, but you can use it to guide it all the way through manufacturing.
It's not just making small measurements on huge mirrors, though. Dr. Kim also develops whole new techniques based on the same fundamentals of profilometry. For example, one of his projects is to expand the size of space telescopes by 5 times using inflatable mirrors. The profile is exactly as important as in the old mirrors, but it takes whole new approaches for whole new machines to work on these new mirrors.
Thanks.